This is part 10 of the series Right Triangles and Trigonometry, and we're continuing on with the example we had started in the last session, and we're solving a right triangle, and we were finding the measure of angles using arc functions. In this case, we had the angle C that we were looking for, and we ended up having to use the arc cosine function, which is the inverse of cosine. And we talked about the fact that arc cosine undoes cosine, and likewise arc sine undoes sine, and arc tan undoes tangent. So what we're going to do now, we could go ahead, and you would, if you were using this to actually solve a right triangle in an actual problem, you would simply use this and the triangle sum theorem to find your third angle. But we're going to do this instructively and try to use our trig functions to find the angle, to make sure that they come out right. So let's try to find the measure of angle B now. We're going to do the exact same thing we did before. Instead of this time, we're starting with angle B. So we have sum, old horse. That's the one we want to use, because remember, we didn't want to use the approximation over here, because using an approximation to find an approximation compounds error. So the first one out of the box was sine. So let's say that sine B equals old horse, 7/13. Now, just as we had before, we have an issue because we have to solve for B. The only way to solve for B, because these two are inextricably linked unless we undo the sine function. Just as this could not be, the C could not be pulled out of cosine except by using the arc cosine function. So here the only way to pull the B away from the sine is to undo the sine by using arc sine. And if I take the arc sine of one side, I've got to take the arc sine of the other. So arc sine undoes the sine. I'm left with B equals arc sine of 7/13. Going into our calculator, we have arc sine of 7 divided by 13, and that gives us 32.57. And if you looked and added these two together, you can see that that's 89 and 0.5. It's going to be really close. It's actually going to end up being 90 degrees. So if we did this again, let's store this, and then let's do this expression again. So there's the cosine, and let's store that in A. Now let's add those two together. A plus B, and they should come out to 90. So you can see that we got the proper value. So our answer was 32.6. So this angle is approximately 32.6. So you can see how nice this symmetry works out, where this angle is 32.6, 57.4, and they all add up to 180. And we have solved this right triangle. So let's go ahead and work out another example. In this example, we have a similar situation, different triangle and uglier numbers, but the same basic principle. We're looking to solve for a side length, and then we're going to find these two angle measures, angle G and angle I. So again, I'm going to go ahead and solve for the side first, and that's going to be using Pythagorean theorem. So we know that the sum of the squares of the legs, so 6.2 squared plus 8.9 squared equals GI squared. We're going to take the square root of both sides. So the square root of 6.2 squared plus 8.9 squared equals GI. And we put that in our calculator. Let's move the calculator over here. Square root of 6.2 squared plus 8.9 squared. And that's going to give us 10.8. So GI is approximately equal to 10.8. Now let's go ahead and find the angles. I'm just going to start with G. You can start with anything you want. Doesn't really matter. Some old horse. Can't use it. Don't have the hypotenuse. Caught a horse. Can't use it. Don't have the hypotenuse. Taking oats away. In this case, it's tangent. So tangent of G equals taking oats away. 8.9 over 6.2. Just as with sine and cosine, tangent has an inverse. It's called arctangent. So arctan of tan undoes the tangent and gets us to G. Then we have to take the arctan of the other side as well. These cancel each other out. G equals arctan of 8.9 over 6.2. Go to our calculator. Arctan 8.9 divided by 6.2. 55.1 degrees approximately. So approximately 55.1 degrees. Now, just as we did before, let's go ahead and use the same method to find I. Again, you wouldn't want to do this on a quiz or a test. You would just take this value and you would store this value. You want to definitely store it, because remember that this is an approximation. If you just lop off all these decimals and just use the 55.1, your answer is not going to be correct. So you would definitely want to store this. So store, in this case I'm going to store it to A, and I'm going to record that I stored that in A. And then you would subtract that from 90. So 90 minus A, and this would be your value. This is going to be the measure of angle I. And so just for kicks, we're going to store that in B. So we'll check back to see if that's correct. But let's go ahead and calculate it using our trig functions. So some old horse, no. Caught a horse, no. Taking oats away. It's tangent again. So the tangent of I equals taking oats away. 6.2 over 8.9. Notice they're reciprocals of each other. Interesting. Now, we're going to undo tangent by taking the arctan of both sides. Arctan undoes tangent. I equals arctan of 6.2 over 8.9. Let's go back into our calculator, and arctan of 6.2 divided by 8.9. And you can see we get the exact same result. And the reason you don't want to do this on a test is because obviously this takes longer than it does just to subtract the two numbers. So you want to streamline your time on tests. But anyway, we have 34.9 is our approximation. So approximately 34.9 0.9 degrees. And that is a summary of the trigonometric functions. So we had sine, cosine, tangent. We had arcsine, arccosine, and arctangent. And always remembering that to solve a right triangle means to find all the missing sides, all the missing angles. Never use an approximation unless you have no choice. We're going to be working on examples that don't give us a choice. But unless you don't have a choice, use known values instead of approximated values. All right, let's move on to the next section. In this section, we're going to investigate the idea of cofunctions. Now, frequently in our study of right triangles, we realize that the acute angles are complementary. And that word complementary means the angles add up to 90 degrees. That's where the origin of the term cofunction, co standing for complementary. So we're going to be dealing with the idea that sine and cosine are complements of each other. Notice the spelling of the word. Sine, cosine. Sine and cosine are complementary functions of each other. Let me exemplify that graphically. Here I have the graph of sine. This is the sine function. If you were to graph that on your calculator, that's what it would look like. The cosine function is this function here. And the difference between them is they are shifted 90 degrees apart. This pi over 2 indicates 90 degrees. So this is 90, 180, 270, 360 degrees. If I were to translate the sine function 90 degrees, that is, move it out of phase 90 degrees, we would have the cosine function. So as I translate it, you'll see that sine and cosine have the exact same shape. They're just shifted 90 degrees apart from each other. And that's the reason that in our previous examples, we got the same numbers when we used the complementary angle and the different function. When we used the complement of the acute angle and the cosine versus the original angle and sine. So they are complements of each other. Now that idea sets up the cofunction identities. That is, the sine of an acute angle is equal to the cosine of its complement, and the cosine of an acute angle is equal to the sine of its complement. For example, if A and B are complementary, then A equals 90 degrees minus B, and likewise B is 90 degrees minus A. So therefore, the sine of angle A equals the cosine of 90 minus A, and the cosine of A is equal to the sine of 90 minus A. For example, sine of 30 equals the cosine of 90 minus 30, which is, of course, the cosine of 60. And the cosine of 30 is equal to the sine of 90 minus 30, which is sine of 60. So we can verify that really quick in our calculator. We can say that here the sine of 30 is 0.5, and the cosine of its complement, 60, is 0.5. Likewise, the cosine of 30 is 0.866, blah, 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 and the sine of its complement is going to be the same number. So the sine of an angle is the cosine of its complement, and the cosine of an angle is the sine of its complement. So let's look at a couple of quick examples. Here we want to rewrite the sine of 47 in terms of cosine. So sine of 47 is cosine of its complement, so 90 minus 47 is cosine of 43. Rewrite cosine of 52 in terms of sine, so the cosine of 52 is the sine of its complement, and so the cosine of 52 is the sine of 38.